It's a pleasure to be here. I saw the show of hands for extra class hams. How many hams are in the audience here, just generally? Oh, wow. Fantastic. Okay. I feel right at home. I'm not a communications engineer. And my experience with new radio is just kind of dabbling with it as a hobbyist with SDR Play, and actually put together a little single sideband decoder to play with for ham radio. So that's my experience there. But what I want to talk to you about is what was going on 50 years ago now was, of course, 50 years ago in July was the anniversary of the Apollo 11 mission. And unless you were living in a cave somewhere, you couldn't have missed that. It was on all the media outlets and everything. And we had a special event operation, kind of a NASA-wide one for amateur radio. But it's kind of nice to look back and see how this was done. It always amazes me as we are trying to develop the capability to get back to the moon now, and I'll talk about that at the end of the discussion here. Looking back and seeing how they did it 50 years ago just never ceases to amaze me. There was, the technology back then was totally different and, not nearly as capable, but let's see, let me move along to the next slide here. So, of course, this is a big deal here in Huntsville because we built the Saturn V here. I didn't. I was 14 years old at the time. But that's one of our great legacies here in Huntsville, and we're building the next great rocket as well, the Space Launch System that I'll talk about. And so what we were seeing 50 years ago was this.
That's one small step for man, one giant leap for mankind. Columbia, this is Houston, ALS, over. Houston, Columbia on the high gate, over. Roger, the EVA is progressing beautifully. They're setting up the flag now. I guess you're about the only person around that doesn't have TV coverage of the scene. That's all right, I don't mind a bit. They've got the flag up now, and you can see the stars and stripes on the lunar surface. Are you getting a TV picture?
All right, so that's what we saw and what we heard 50 years ago, and I started researching this to figure out how did they do it. What was the hardware, what bands were they using, and that's what I'll talk about today. Kind of the rough outline here is we'll talk about how the audio got back, and the key is USB, and that is not upper sideband, as you'll see. They'll talk about some amateur radio involvement here. We call this extreme shortwave listening. It wasn't shortwave, it was S-band, but extreme S-band listening by hams. And talk about some of the options for the comms. Something that you may have noticed in that clip right there was that was Armstrong and Aldrin on the surface, and of course they were talking to mission control, but then you heard them also talking to Mike Collins, who was in the command service module orbiting around the moon at the time. And so I'll talk about kind of how that was done, what some of the architecture there was, how we got color video out of that really grainy, awful-looking black and white there. And then I'll talk about what our plans are for the future, what we're going to do next. So let me see if I can do this. First of all, one of the iconic things that we all remember, and anytime somebody's kind of simulating air-to-ground communication, they always put the beep in there, right? So that's called a Quindar tone. And that's the name of the company who developed these Quindar tones. And they were used really just push to talk. That was the idea. So there was, I'll talk about the ranging capability of the system in a moment, but because they wanted to keep a continuous carrier going up to the command service module, they had to keep and they didn't want the Capcom and mission control to be live all the time going through that system. They had this tone system called Quindar tones, and so when he pushed to talk on his headset in mission control, the intro tone went out, and then when he released the push to talk, the outro tone went out. And so that way they were able to keep that line going, keep that audio going, but not have a live mic for him all the time. And let's see if we can play this here. The intro tone, is at 25 hertz. And the outro was 50 hertz lower. You can tell the difference there between the intro and the outro. So that was just used to key the ground stations, which could have been as far away from mission control as Australia, to tell them, okay, now take the audio coming from mission control and send it up. So that's all that was. This S-band carrier was, as I mentioned, sent up kind of constantly so they would be able to do ranging, and they used a pseudo-random number code for the ranging. And I'll talk about that a little bit more as we go along here. All right, so the Snoopy cap is what the astronauts use there, and you can see what the inside looked like, a couple of headsets, and then the two boom mics. And you can see why they were called Snoopy hats at the time. Snoopy, of course, and the Peanuts comic strip was very popular back in that time period. I listened to a lot of the audio and kind of the full mission audio while they were on the surface of the moon during the anniversary through this Apollo in real time. Anybody else familiar with that? Anybody else try that out? Yeah, that was extremely cool, and it's still out there. And I have a link for it at the end here. So on that, the July 20th, that evening, you could listen in real time of what was happening exactly 50 years ago. And so I watched the whole EVA, and I remember Aldrin, they kept having a hard time hearing him from time to time. And so he finally said, well, one of these microphones is in my mouth, and I can't do anything about it. You know, it was kind of, you can't take your helmet off, obviously, when you're on the surface there to move it. So they had the two mics, and so that was the audio to and from the crew. So this USB, that's Unified S-band system. Now what they had before this, according to my little historical research, during Mercury and Gemini programs, they used HF, VHF, UHF. They kind of had, and C-band for tracking, radar transponders for tracking. So they had all these different radios, all these different systems on the spacecraft. And some of them were telemetry, some of them were for audio. And so they decided with Apollo they needed something smaller and lighter. You're going all the way to the moon. You don't want to carry a whole bunch of different radios with you. So they came up with this unified S-band system that sort of did all of it. It had voice, digital, the ranging signals from the ground to the spacecraft. And in spacecraft to ground, they included telemetry, TV, the biomed data. They had an emergency voice channel and even an emergency key. They could do CW. They could do Morse code if they needed to. They only tested it, I think, on Apollo 7. Fortunately, they never needed it. But if they'd had some other problems with antenna pointing or something like that, they actually could do Morse code. They were able to communicate with the command module. That was where most of the data, of course, flowed from. The lunar module and the Saturn S4B. I should mention that all of this information here is from a NASA technical memo, and it was actually a conference paper back in 1966. It describes this system. And if you want to look that up, you can probably, what happened? I lost a signal there. You can look that up and read more detail about how this works. And I want to challenge you guys. I don't know a whole lot about new radio and how you use it in academia, but this would make a very cool class project, I think, to tell the students, use these modern tools that you have, these modern software tools, and just simulate this whole S-band, unified S-band system. So I'll just throw that out there as a challenge of something you may want to try. I kept thinking as I was reading about how they did all this stuff with analog circuitry, how much easier it would be today. All right, so that's what it looked like. That was one of the radios. You can see a little scale there. I think that's a 6-inch scale. So it's fairly small, but packed, a lot of information packed there. That was based on a design that I think Jet Propulsion Lab had kind of come up with for some of the unmanned spacecraft. Goddard was involved, Collins Radio, Motorola, some of the big names were involved in that. I don't know why we keep losing. Yeah, maybe that's it. That's right. We're in LOS. Okay, it's over here. So, all right. Yeah, there's our modern technology for us, right? All right, so both the spacecraft had a lot of antennas on them. You can see there were Omni antennas body mounted on the command service module. And I'm going to try to avoid using the pointer too much because there's so much action here. But there's some Omni antennas out there. You can see the big the 4-bay dish antenna there. And of course that was for the high rate data. The lunar module had Omni antennas. It also had VHF antennas, and that was used during the EVAs, during the moonwalks, to talk to the crew so they could relay their signals back to Earth. And so there's some VHF antennas there, an S-band high gain antenna on the lunar module up here, and then they had a radar antenna as well that they used for the rendezvous when they linked back up with the command service module and before they left the moon. All right, the ground antennas, there were two classes of those. There was a 30-foot dish and an 85-foot dish, both Cassegrains, and you can see the gains and the beam widths there and the acquisition antennas. But I think the interesting thing is they were 20 kilowatt transmitters, used klystrons. There you can see the preamps, parametric amplifiers, and frequencies, S-band, about 2.1 gigahertz. There were subcarriers that were used, and we'll see a picture of this in a moment of where they put the voice and the data, but those are the different subcarriers. And you can see with the, this is uplink, of course, but the downlink is very similar. They had a 1 kilohertz sync tone, and they had this sine wave biphase modulated. I guess we're still using something kind of like that these days. And then the ranging code. And this looked to me like, reminded me a whole lot of either radar or GPS, you know, where you have this pseudo-random number code. And what they did here is they modulated the S-band signal with this, and they had two different ones, 70 millisecond one when they were in close to the Earth, and then a 5.4 second one, which, you know, repeated every 5.4 seconds. Well, the range time to the moon is only 1.5 seconds, or round trip's about 3 seconds. So they could have used this even farther out past the moon without ambiguity. So there's this PRN code that was transmitted up, and then they just turned around and transmitted it back down. And by correlating those on the ground, they could figure out how far away the spacecraft was to within a few meters, I think is what I read there. So that's pretty accurate. Also, the carrier was, they had a phase lock loop, and then, you know, used that to generate the signal coming back to Earth. And by tracking the frequency of that carrier, they were able to get the range rate to within, I think it was, 10 centimeters per second or something like that. So the very precise range and range rate, and then of course they had the ASL from the ground tracking antenna. So with that information, and assuming ballistic trajectory, you know, that's how they tracked to the moon. So very simple but clever process. All right, that's what one of the 85-foot ground stations looked like in Australia. And now here's the spectrum of the downlink. And I will have to kind of point at this a little bit. There's the carrier. It was a phase-modulated carrier. And this document, this TM technical memo document, talks about they tried to keep the modulation index kind of low so you had a nice, strong carrier to lock onto. They didn't want to lose the carrier and all the other signal there. And you can see the voice and telemetry subcarriers. They tried to put that pretty close to one of the nulls there in the PRN code modulation. And then they had these other modes where they could kind of turn off the tracking PRN code and just have the television and then the voice and the telemetry, or they could turn everything off except for the voice. And then here is that CW, the Morse code, 512 kilohertz subcarrier they could use just for emergency key, they called it. So the voice, we got things like that. And I think also in the voice signal was the biomedical data. So this is the heart rate of Buzz Aldrin as they were on the moon. And that's the telemetry, of course, that came back, all the information that As you saw Apollo 13, everything that went, the screens went blank, or they lost all the data, you know, when they lost comm after the explosion. And then the tracking, talked about that. And of course the video, and then that emergency key. So that's all of the information that was just packed into that one S-band signal. Now the spacecraft radio characteristics, it used a traveling wave tube, TWT. 20 watts was a primary mode. They also had what hams call a QRP mode. They could run 5 watts if they needed to. And then we talked about the antennas already. There's all the frequencies. And it's interesting, they use this 240 divided by 221 as the ratio of the uplink to the downlink. And so they had that kind of wired in very carefully so that they could use the Doppler to figure out the, you know, the velocity of the spacecraft. And there's the info on the voice and telemetry subcarriers and the television that I'll talk about a little bit more. All right, of course, hams had to get into the act here, and radio amateurs have, for a long time, done really the extreme part of ham radio is called moon bounce, or Earth-Moon-Earth. And this is simply bouncing a communication signal off the moon, just having it scattered off the moon. It was all done with Morse code. Back in the day, it's done with digital modes now. Something called JT65 is very popular for that kind of thing. But the guys who were ready to do this back in the 60s and 70s thought, well, let's see if we can hear the radios from Apollo. And so there were 2 of them that published in this QST, that's the Amateur Radio, American Radio Relay League, ARRL. I'm an ARRL member, I should remember that. That's their main magazine. So back in 1972, they had this article about how 2 hams actually heard Apollo 15, the command service module. And both of them, if you go through and read the account there, ARRL members can go look at the archives and find this magazine here, June 72, and read about this. It's fascinating. Both of them kind of independently did this, and neither of them were expecting to hear the signal, and they didn't have their tape recorders running, so they weren't able to record it. They just heard it kind of come through the speaker all of a sudden, and then got more intentional about it later. So that's who they heard. That was Al Warden, who was on the command service module, the command module pilot. And so the 2 were K2 RIW and W4HHK, and I love this this one here. The antenna feed was an American paint can and a Scottish oatmeal can. Now, I don't know, there's something magical, I guess, about the dimensions of a Scottish oatmeal can. How he came by that, I'm not really sure, but to build the antenna feed. And so both of them had kind of similar, you know, big dishes with their feeds there. And it said that the command module at the time was it was about 13 watts, so they were able to hear 13 watts at S-band with these big dishes. So here's a block diagram of K2 IRW system, and I'll zoom in a little bit here and show you that you know, there's parametric amplifiers and spectrum analyzers and all kinds of stuff in there. But there's an Amico 2-meter converter, which I know a lot of hams used at the time, a Drake receiver, and a modified night receiver. So it's good to see some good old ham gear in the system here. Now they tried again with Apollo 16, you know, kind of from the success of this, and it's really amazing what was accomplished here. First of all, they were able to detect the lunar module carrier, and from the Doppler, these guys could tell when it set down on the surface, when it quit moving. Now, your conspiracy theorist would have to explain that. I guess that could have been fake too, right? You know, we could have sent a spacecraft to do the same kind of thing. But that's pretty amazing they were able to do that. They also detected the uplink signal, this 20 kilowatt signal coming from these big dishes. They detected that scattered from the moon. So this is the moon bounce thing. Well, you know, hams can only do, what, 1.5 kilowatts. And so they were able to, you know, they were doing moon bounce back in that time frame with 1.5 kilowatts. So it seemed like, I guess that's pretty easy to do with 20 kilowatt uplink. And then there's a 1 watt signal from the ALSEP scientific packages. This is what each of the Apollo crews left on the surface of the moon that were seismometers, and I've got a picture over here in a minute, I won't go through all that. But they were able to detect that 1 watt signal coming from those things. So I think that's pretty amazing. So that's what the ALSEPs look like. They had little radioisotope thermoelectric generators on them to run the seismometers and magnetometers, and you can see all the other instruments there. And there's the S-band antenna there pointed at the Earth, 1 watt, and they detected that. So pretty amazing. All right, so there was a lot of reconfigurability in the system, just in case they had problems or they needed to do something a little bit different. And these are just a few of the options here. So they could use VHF to talk between the lunar module and the command service module, full duplex, 2 different frequencies. And then if they needed to talk to the command service module when it was below the horizon, they could do that through the Earth. So S-band up to Earth and then out to the command service module. And think about this for a second. Each leg of this took 1.5 seconds, and so you got 4 hops essentially here. So there's 6 seconds that delay that you'd have to deal with. And then there's the VHF comm between the crew members, the LIM, and then that was sent back up and back down, from the S-band system. I noticed that I think Apollo 11, they did not deploy one of these kind of dishes here, and again, in listening to the real the 50-year plus real-time audio, I did hear Armstrong ask, "Do you have a good TV signal?" And what he was asking was essentially, do I need to bother setting up this antenna? And they were getting enough video, and of course it wasn't great. It was that slow scan. Whoops, back up. Kind of grainy stuff. That was coming through the S-band antenna on the lunar module, not one of these dishes here. Now with Apollo 12, they switched to that kind of dish. I don't know if you remember Apollo 12. They kind of accidentally pointed the camera at the sun, and that was the end of video from that mission. But they did have that dish set up, and we got a little bit of video kind of early on. And then there's all this, once they had the Lunar Rover, which was also developed here at Marshall, they had additional communications capability. It had its own S-band dish, and could send video back as well as the, repeat the VHF audio from the crew. All right, so how did they do that video? Well, it was this ancient Vidicon technology. I think the camera on the left there in the guy's right hand is the onboard, and I saw a picture of the back of it, and I think that actually had a monitor on it so they could see what they were looking at. And of course that was a CRT type monitor back then. And then the one on our right there is the surface camera, and that's what was used to show us the video from the surface of the moon. The Apollo 11 video was it was all black and white, 10 frames per second, slow scan, so that kept the data rate down, kept the bandwidth down, only 320 lines. And then to get standard video that they could distribute then to all the news outlets so that Walter Cronkite could share the video with us, they actually had a camera looking at the screen on a ground station that was looking at the slow scan 10 frame per second thing. They recorded it to a magnetic disc and replayed it 5 times each to get the 30 frames per second or 60 fields per second of standard video. So just amazing to think that you had a camera looking at a monitor and this disc and doing all this shenanigans to get us some standard video. Pretty clever. All right, so we saw black and white from Apollo 11 and 12. I can't remember when the color came in. I think maybe 12 might have even been a color camera, but how would they get the color from a black and white Vidicon? Well, TV cameras of that day were pretty big, and they had 3 different Vidicons and color filters in front of them. They use beam splitters, so they take the light coming in and split it up into 3 colors and run it through some optics into these Vidicons, and then you'd have the red, green, and blue signals coming out. And that obviously was not going to work for sending into space, because you would have probably had to leave one of the crew members behind if you were carrying something that big with you. And keeping all of that stuff aligned with all the launch loads and vibrations, I'm sure would have been really tough. So they came up with this scheme where you spin a color filter wheel in front of the black and white camera. And they had 2 red, 2 green, 2 blue filters running at 10 revolutions per second. That ends up giving you the 60 fields per second that you want. That was a wider bandwidth signal. And this report said that they had to do significant filtering to keep that from interfering with the other S-band components, all the telemetry and ranging and all that stuff. So a lot of analog filtering going on. Then they used videotape to correct the video sync for Doppler. Obviously, these spacecraft are moving. The video sync signal is moving along. And so they used a videotape system for that. And then another magnetic disc recorder to spin at the proper rate there, recorded the R, G, and B on 6 separate tracks, and then they read them back simultaneously to generate the color. And so that's so clever to come up with that kind of thing. And I'm not sure if you can tell exactly there, but if you look very carefully, you can kind of tell that thing was spinning. Now, this is one of the Lunar Rover videos of the launch of the ascent module back up from the surface. And if you look right here, there's a blue, green, and red. So that was some piece of debris that was blown off the upper stage, or I mean the lower stage, the descent module, as the engine ignited. And you can kind of see that there's blue, green, and red here. So that particle was moving fast enough that you captured it in one color filter at one point, and then the next color filter at the next point, and the next one at the next point. So you can kind of tell how that worked there. So it was fine for guys walking around the surface, but for very dynamic events like that, you see some artifacts, obviously. So you can tell that's how it worked. I think they used something similar to this on shuttle during the early days. They must have gone to CCDs at some point, but because I remember seeing some kind of dynamic events of some piece of junk floating away from the shuttle and seeing the red, green, blue components of it. So I think that was used early on in shuttle. So you need that wider bandwidth, need better signal for the S-band, and they had this deployable antenna that they could set up on the surface. And then when they had the Lunar Rover, starting with Apollo 15, they had the little antenna. And every time they parked the rover, they had to get out and point that antenna back up toward the Earth. And then the ground could take control of the camera. You can see the camera right there. They always kind of pointed it down and back to keep the dust off of it. But still, you would see them during most of these EVAs pull out a paintbrush and dust the dust off the lens so that we get a good view from Earth. But the ground controllers could pan, tilt, and zoom that camera and watch the crew as they were walking around.
I was strolling on the moon one day in a merry, merry month of December. Now, May, when much to my surprise, a pair of bunny eyes. Oh, this is a neat way to travel. Isn't it great?
So they're panning and zooming here from Earth.
I like to skip along. Not me, boy. Skip.
It's amazing. What an amazing time that was. All right, so that's what the lunar surface assets look like, and I don't remember which mission. This could be 11. There's the camera that was looking back at the lander and the part of the ALSEP system there. So that was then, and we were just lasted, well, I guess from 1969. The plaque on the left there is the one from Apollo 11, Here men from the planet Earth first set foot upon the moon, July 1969 AD. We came in peace for all mankind. And then Apollo 17, in December of 1972, here man completed his first explorations of the moon, December 1972 AD. May the spirit of peace in which we came be reflected in the lives of all mankind. And we haven't been back yet, and that's kind of a shame. We've had a few fits and starts here with different administrations of saying, let's go back to the moon. We've got a pretty good head of steam now, but it all depends on the political will and the funding and all that. But I want to talk to you a little bit about what our plans are for returning to the moon now. The program is called Artemis, and I've got a video here at the end. They'll probably talk about this, but that's the twin sister of Apollo. That's pretty cool. Our plans are to have boots on the moon is the direction that we were given by 2024. That's pretty ambitious. We have the rocket, we have the capsule. The lander is under development now. And we're not there yet by any means, but I've never seen NASA move so fast on something, I'll tell you. It's been dizzying, the speed at which we're doing this. So back in December of 2017, there was a space policy directive from the White House to return to the moon and onto Mars. And the plan at the time was by 2028, get to the moon. Then in March, Vice President Pence was here for the National Space Council, and right over here at the Space and Rocket Center, and said, okay, we want you to do it by 2024. And to land humans near the lunar South Pole. And I'll talk about why that's interesting in a moment. You can do these, go back in a hurry and land and, put down the flag and take pictures and one small step and all that kind of stuff. But the idea here is to make this sustainable so that we can keep doing it, that we don't just do these little camping trips and, real quick ones. And so I'll tell you a little bit about the architecture for doing that. It will be done with something called Gateway, which you'll see in a moment, and the human landing system, which may have multiple elements to it. I think there's getting ready to be some contracts let here in the near future. There's already some studies going on by contractors, but there may be a transfer, descent, and ascent elements. And they'll all be aggregated or kind of assembled at this gateway. And then hopefully the ascent element will be reusable, refuelable, and maybe even the transfer element too. The space launch system that we're developing now, which will be more powerful than the Saturn V, and this Orion capsule will ferry the crew and some of the hardware, and then there will be commercial launches to transport some of the hardware and the logistics. So that's kind of in the planning right now. Remember Apollo, the way we did that was put it all on one rocket. So you had the command service module and the lunar module all stacked up there and send it all at one time, and so all of your capability was sent at once. And the idea here with the Space Launch System and Gateway is to send those pieces individually and assemble them in lunar orbit. So SLS, this may look familiar. That's kind of like an external tank on steroids from the shuttle, just bigger. And we're testing those elements right now out at Marshall, doing structural tests on them. The boosters on the side here are like shuttle solid rocket boosters, only longer. They got an extra segment in them to make them more powerful. And the engines are shuttle main engines, kind of upgraded a bit, but there'll be 4 of them instead of 3. So with all of this stuff, you get the extra power you need to get to the moon. There's an upper stage here. This initially will be based on the Delta cryogenic second stage, the DCSS. It's called the interim cryopropulsion stage here, but there's also development going on now for the exploration upper stage, which is a more powerful version of an upper stage. And up on top of it, the capsule, the Orion, and the service module, and the European Space Agency is providing that service module. So those are the pieces. That's what Orion looks like. Now this shape may look really familiar to you. This is exactly the same aspect ratio, I guess you'd call it, or outer mold line shape as the Apollo capsule. I remember when they started development of this, they started looking around, what's the best shape to use for re-entering from the moon at these very high speeds. And it turned out that what they came up with for Apollo was pretty doggone good. So they stuck with that kind of shape. It's bigger. It'll carry 4 crew members and it can stay a whole lot longer at the moon. It has solar panels instead of the fuel cells, which kind of had limited lifetime on Apollo. They run out of hydrogen and oxygen, so you get much longer stay times with this hardware. And then that's what the gateway and the lander looks like. And the gateway portion is this. There's a power and propulsion element, which has these big solar arrays, and that'll have ion engines on it. So they'll be able to test that technology for changing the orbit around the moon with that. Then there's something called a mini-hab here that is sort of a pass-through to go from a logistics module. So that's hardware and food and all the consumables that will be brought up on a commercial launcher. And then this is what the lander looks like. Kind of vaguely reminiscent of the lunar module, but a whole lot bigger. There is this transfer element that you need to get from the orbit that Gateway is in, which is called a near rectilinear halo orbit. It's a very eccentric orbit around the moon, 75,000 kilometer apollune. So it'll be in that orbit. It doesn't take so much energy to get to that orbit. So it's kind of easier to assemble the hardware there. And then you use this stage to get from that orbit down to low lunar orbit and land. There's the descent module, so it'll have the legs on it, to sit down on the surface, and an ascent module. And that's where the crew will be, and that's the part that comes back up and docks with the gateway. And then the crew can climb in Orion and come home, bring the moon rocks home, and all of that kind of thing. So that's the idea. Now, Gateway Phase 2, after the 2024, would look like this, and that actually has a habitat modules in it, so you can have crew there for quite a while, several weeks at a time, maybe up to a month, I think is what they were talking about. The idea of that is you don't really need that to get to the moon, but that's probably what a Mars vehicle is going to look like, very similar to that. With an ion engine on the back of it and habitat modules and a capsule. Now you probably have to send some kind of ascent hardware to Mars ahead. But the idea is not just to get to the moon with this hardware, but to also test out the technologies you need to get to Mars. And that's what the lander might look like, sitting on the south pole of the moon. Now, it always bothers me. I'm an astronomer by training. And you see these pictures from the moon, and there's the Earth hanging right down near the horizon. And you don't see that from the Apollo sites. It's always up high in the sky because of the way the moon's tidally locked to the Earth. But in this case, we will have these kind of views because the plan is to land at the South Pole. Both the South Pole and the North Pole have permanently shadowed regions. And these are craters. This is a lighting map based on Lunar Reconnaissance Orbiter, which is a spacecraft that's been operating since 2009, I think, in orbit around the moon. I'm pointing at this one because it's a little darker over there, so I hope you guys over there can see what's going on. So LRO's been making measurements. It has an altimeter, and they build these digital elevation models, and then they fly the moon around the Earth and look at how the sunlight shines on it. And the bright areas are regions that get a whole lot of sunlight throughout the year. And the dark regions don't get any sunlight. So when you get to the South Pole, because of the moon's orbit, it's very low inclination, and the moon is only tilted about 1.5 degrees from its orbit, there are regions that never see any sunlight. And there's very good evidence that there's water mixed in with the regolith, mixed in with the moon dirt there. And so when you have water, and you can mine that, and that's no easy trick because it's so cold, it's about 30 or 40 degrees above absolute zero Kelvin in these craters. But if you can get that water out and use some solar energy, you can crack the water into hydrogen and oxygen, there's rocket fuel. So that's the idea, is to go to a place where there may be resources that we can actually use there. And the South Pole is right around in here, I think, right along there. So it'll be somewhere in that vicinity, but possibly on that ridge or somewhere nearby where that first landing occurs. All right, now I have a video here. I think that will play.
50 years ago, we pioneered a path to the moon. The trail we blazed cut through the fictions of science and showed us all what was possible.
It's very pretty out here.
Today, our calling to explore is even greater. To go farther, we must be able to sustain missions of greater distance and duration. We must use the resources we find at our destinations.
See if you
We
recognize
must overcome
the narrator
radiation,
too.
isolation, gravity, and extreme environments like never before. These are the challenges we face to push the bounds of humanity. We're going to the moon to stay by 2024, and this is how.
This all starts with the ability to get larger, heavier payloads off-planet and beyond Earth's gravity.
For this, we designed an entirely new rocket.
The Space Launch System. SLS will be the most powerful rocket ever developed.
And with components in production.
And more in testing?
This system is capable of being the catalyst for deep space missions
We need a capsule.
that can support humans from launch
through deep space and return safely back to Earth.
For this, we've built Orion.
This is NASA's next-generation human space capsule.
Using data from lunar orbiters that continue to reveal the moon's hazards and resources.
We're currently developing an entirely new approach to landing and operating on the moon.
Using our commercial partners to deliver science instruments and robotics to the surface, we are paving the way for human missions in 2024.
Our charge is to go quickly and to stay, to press our collective efforts forward with a fervor that will see us return to the moon in a manner that is wholly different than 50 years ago.
We want lunar landers that are reusable.
That can land anywhere on the lunar surface. The simplest way to do so is to give them a platform in orbit around the moon from which to transition.
An orbiting platform to host deep space experiments and be a waypoint for human capsules. We call this lunar outpost Gateway.
The beauty of the Gateway is that it can be moved between orbits
It will balance between the Earth and Moon's gravity.
in a position that is ideal for launching even deeper space missions.
In 2009, we learned that the moon contains millions of tons of water ice.
This ice can be extracted and purified for water. It can be separated in oxygen for breathing or hydrogen for rocket fuel.
The moon is quite uniquely suited
to prepare us and propel us to Mars and beyond.
This is what we are building.
This is what we're training for.
This we can replicate throughout the solar system.
This is the next chapter of human space exploration.
Humans are the most fragile element of this entire endeavor, and yet we go for humanity. We go to the moon and on to Mars to seek knowledge and understanding and to share it with all. We go knowing our efforts will create opportunities that cannot be foreseen. We go because we are destined to explore and see it with our own eyes. We turn towards the moon now, not as a conclusion, but as preparation, as a checkpoint toward all that lies beyond. Our greatest adventures remain ahead of us. We are going.
We're going.
We are going. We are going. We're going.
So you can find any of these slides on the Artemis mission or that video on NASA.gov. You can go look for that. Who's the narrator? Anybody recognize the voice? Captain Kirk, that's right. William Shatner. Most of the information that I used today came from this How Apollo Flew to the Moon by W. David Woods. That's a fascinating read. It's really interesting. This guy's done a lot of research, obviously, and figured out how all the systems worked. You can go to this NASA Technical Report Server, sti.nasa.gov, and if you're interested in that technical memo that I got most of the info from, most of the other info from, look for Unified Sband System at apolloinrealtime.org. They have an Apollo 11. I think there's an Apollo 17 out there too. I don't know about all the other missions, but I need to go check that. And then the QST, and if you want to explore the moon yourself, go to QuickMap. If you do this, just Google QuickMap, you'll probably find it, but it's quickmap.lroc.asu.edu. There they have taken all of the Lunar Reconnaissance Orbiter data. That's maps and imagery, thermal data, elevations, all of that kind of stuff, and put it on there, and you can just zoom around. It's kind of like Google Earth, but it's for the moon. And there's really good scientific information there, but it's really interesting to be able to see that. And zoom in on the Apollo sites, and you can see where the descent module is sitting and where the tracks for the rovers were. And you can even see tracks where the astronauts walked, because it disturbs the regolith enough to change the brightness or the albedo. And then there's something kind of similar called trek.nasa.gov as well. So this is an exciting time. It was an exciting time 50 years ago, but it's a pretty exciting time now. We just have to keep the momentum up and keep the funding and all of that kind of stuff. But we've really got, I think, a workable plan here. And by using what they learned from Apollo, I kept thinking, I sit in the meetings where we're talking about what's it like on the moon now. We've got, at least from a few sites, from 6 sites, what the properties of the lunar environment is like, which is kind of my job. But also we have an enormous amount of data from this Lunar Reconnaissance Orbiter. We have very detailed maps of the South Pole now, and know what the slopes and the crater sizes and rocks and all that kind of stuff are. So I feel like we're ready to go, and then we have the technology that a lot of you guys work on. I think it's doable, and it's an exciting time. So just stay tuned, and we'll hopefully be able to pull this off. So that's all I have. Any questions?
Thank you, sir, for the history and the future of the space exploration. My question is, when you land on the South Poles with the permanent shadows, how will you get solar energy there to power the equipment?
Yeah, that's obviously a problem. We can't land in one of those craters. I think they're going to have to land on one of the permanently illuminated, or they call it perpetual illumination or something, regions nearby, and then probably send robots down into those craters. Yeah, the spacesuits aren't designed for that kind of cold, and so it'll be a while before anybody goes down in one of those craters or any hardware goes down there. But the idea is to land nearby, and then you're close enough that you can have your other assets, bulldozers and such, go down and bring back the water.
While I ask, Daniel, can you please start setting up your gear? So you had a really cool thing, I thought, the participation of hams during the original Apollo mission. So I'd be curious to know, will the Artemis mission have any opportunity for hobbyists or enthusiasts just to get involved, just observe, or any kind of participation, and maybe even something that we can, I would say there's probably experts here, but we could maybe take elsewhere, like into schools and something like that. Is there anything like that?
Well, that it started with the Shuttle Amateur Radio Experiment, or SAREX, and then on Space Station we have this amateur radio on ISS. This has been very popular. I think there are plans to put something like that on Gateway. It won't be something you can use your 2-meter handy-talkie to talk to over that distance. What I've heard, it may be X-band, and there'll probably be some digital form of communications. I don't know the details of that. So that'll be specifically for amateurs. I think the comm system will probably be pretty similar to what's used on Space Station now. So that's probably KU band. I know it's K-band anyway, and some S-band. So I don't know how much hobbyist involvement there can be there, like there was back then, where they could actually hear the FM signal. But certainly there are plans for amateur radio on the Gateway. I haven't heard anybody talking about amateur radio on the lunar module. I think weight is at such a premium there that that's probably not going to happen anytime soon. But sometime it possibly could. So I would love to have a repeater on the moon, right? So that'd be great.
Hi, thanks for the talk. So when you're talking about the Gateway module, I noticed one of your bullets was specifically about designing around and incorporating open architectures and frameworks, which obviously this conference is all about.
Right.
So I'm interested to hear a little bit more about that and what NASA's thoughts are and their role in the open source community.
What I have seen so far, it was not in the software area, but it was, they've got a set of standards that they put together for any hardware that goes to Gateway, and those are open standards. Now that's like life support systems and command and data handling and you know, the type of Ethernet they're going to use and all that. I think probably most of the software, that's all, you know, flight software, and that's very rigidly controlled. Although I think, aren't they using Linux on space station now? I think I heard that some of the laptops may be Linux. I'm not positive about that. Don't quote me, please. That's when I've heard, I think that bullet was addressing specifically those standards that were put out that they're kind of hardware standards primarily. But I don't know, that's a good question, and that's something that we may want to think about. I'm not sure who to ask about that, but I know that the type of horsepower you have in the room here could really contribute to that, you know, the whole program, and we need that kind of horsepower, so yeah.
I heard NASA had done some tests of high bandwidth communications using lasers. Can you speak to that a little bit?
Yeah, I don't know much about that. I know that the LADEE mission, which I had some involvement with, that's a Lunar Atmosphere and Dust Environment Explorer. I think it had a laser comm system. And again, I'm not a communications guy, but I hear, you know, discussion of that. And I know that they were talking about, you know, looking at that for Gateway as well, but I really don't know where that is right now. I think it was successful for LADEE. If you look up the LADEE mission, you'd probably find some stuff on that. But I think they had some really high data rates, and, you know, so it looked very promising. And especially space-to-space communication. That's where it really shines, I think, because, no pun intended, because you don't need to worry about, you know, getting through the atmosphere kind of thing. So, yeah.
You mentioned mining water resources on the moon. How common is this resource on the moon? Is it sustainable? Is it like reproducing itself somehow? Or is this something that's eventually going to run out?
Yeah, where it comes from is meteoroid impacts, and that's something else that I do in my day job, especially cometary material, because there's a lot of water in that. Now, these things are impacting between 10 and 70 kilometers per second, so a lot of it just goes away. But there's enough of it. They think the reason that we have that there is because of these impacts. You get some of the molecules kind of bouncing around the surface, and these are cold traps. That's a place where it's so cold that if a molecule gets in there, it may stay. And so over billions of years, you build up some of that. Yeah, if we started mining it, you know, really fast, I'm sure we'd use it all up and it'd be gone. But I think it'd take a really long time to do that. It's not really well understood just how much is there, and that's part of the reason for doing this research, you know, sending people there, sending robots down. But from measurements of neutrons coming back up from the surface, and then there was back in, I guess it was 2009, the L-Cross mission. That was the upper stage that sent the Lunar Reconnaissance Orbiter to the moon. They deliberately smashed it into one of these permanently shadowed craters and observed what came out of it from a little shepherding spacecraft from the Earth and then from LRO as well. So we know that there's water there, but I don't think they know exactly how much, or maybe some other stuff there too. But yeah, it's an area of active research for sure. Any other questions?
It looks like there's no more questions. Before you walk off stage, I would like to thank you. We have a reward for all our keynote speakers, our keynote speaker award, and our keynote speaker challenger coin. Thank you very much for talking. It was very interesting.
It's a pleasure.
Another round of applause.
Thank you.